So in today's video, we're looking at the first experiment in our second unit of Grade 9 Advanced Science. We're going to be determining the freezing point of a chemical called naphthalene. I have a test tube here that's been filled with naphthalene. It normally comes as a white powder. This has been melted and allowed to freeze several times, so it now has this white crystalline solid in the test tube. We're going to begin by melting the naphthalene completely to turn it into a liquid naphthalene. Then we're going to let the naphthalene cool down slowly as we record the temperature every 30 seconds in order to make a graph of temperature versus time. From that graph, that cooling curve for naphthalene, we're going to determine the freezing point of the naphthalene, the temperature at which the liquid freezes. Now I've got here some setup that are normally used for Grade 9 Advanced Science. Under your sinks in the lab, you have these pegboards. I've turned this pegboard on its side just to make it taller. We also have clamps like this. The clamps have a wing nut on the back. You can turn and take the wing nut off. There we go, spin it, and the wing nut comes completely off. And then you can put the clamp into one of the holes on the pegboard and put the wing nut on the back and tighten it to hold it there. Underneath your bench, underneath the sink, you also have these wire stands. I've put a wire stand underneath the clamp and a beaker from the side of the lab. This is a 250 ml beaker, which has been filled about 2/3, 3/4 full of tap water. We're going to use a Bunsen burner from under your bench to heat that water up to get it to be initially around 90 degrees Celsius, 85 to 90 degrees, somewhere in that range. Now the clamp that I've already attached up here is going to hold a thermometer. I've got a thermometer here, one that's an alcohol-based thermometer, not a mercury thermometer. Mercury would be a silver-colored liquid, and although it's a much more accurate thermometer, mercury thermometers are dangerous if they break. Mercury is highly toxic and is a real mess to clean up. So we're using less accurate but much safer alcohol-based thermometers. I've got a cork with a split in it. We can push the thermometer into the cork and then put that cork into the clamp that's on the pegboard, push it in, and that's going to hold my thermometer like that in my water bath. I'm going to heat the water bath in just a moment until the temperature rises to between 85 and 90 degrees. I want a second clamp though. I'm going to push the second clamp into the pegboard, and I want it slightly above the mouth of the beaker. It's going to hold that test tube full of naphthalene once the naphthalene has been melted. So let me just attach the wing nut on the back of the pegboard. There we go. Tighten it, and that's going to hold my test tube in place. All right, so that's ready to go. I just have to grab a test tube now of melted naphthalene after I've heated my water bath. We'll put it in, then we'll start recording some data. All right, so I have now boiled the water in my beaker. It's been cooling slightly. The temperature in the water bath, so this thermometer here, is reading the temperature in the water bath itself. It's right now around 90 degrees Celsius. I've grabbed a test tube here from the fume hood on a hot plate. The test tube has the naphthalene that is now melted, so it's a clear, colorless liquid, and a second thermometer is placed into there, and that is now clamped and being held in the hot water as well, and it's also around 90 degrees Celsius. Now these thermometers, again, they're not the most accurate, so if they were both recording the same substance's temperature, say the water bath, I wouldn't be shocked if they had a slightly different temperature reading. There's a small error of 1 or 2 or even 3 degrees Celsius with these cheaper alcohol-based thermometers. So now what we're going to do is we're going to start timing. So if you have a stopwatch or if I'm looking at a clock in the lab, I'm going to record the initial temperature at time 0, and then at every 30-second intervals, half-minute intervals, I'm going to record the temperature both of the water and of the naphthalene. Now you know, I hope, that water freezes at 0 degrees Celsius. I'm in a chemistry lab right now where the room temperature is approximately 20 degrees Celsius. So as this cools, the water temperature is going to drop down, but it's not going to come anywhere near the freezing point of water. So the water basically is simply going to cool down from hot water to cooler water. The naphthalene, though, that's in that test tube is right now melted. You saw the liquid naphthalene. I'm going to cool it, and as I cool it, it's going to freeze. It's going to become solid naphthalene, and we're going to see what happens to the temperature as it freezes. So we'll be recording 2 different temperatures every 30 seconds. So we'll have a column for the water bath temperatures and a separate data column for the naphthalene temperature, and then we'll be graphing both sets of data on the same piece of graph paper and comparing the 2 curves that we get. All right, you'll notice that I've changed our setup here. For the sake of the video, I'm going to use temperature sensors, which are connected to a LabQuest interface, and you can see on the iPad screen the temperatures displayed. The red temperature is the temperature that is of the sensor recording the naphthalene's temperature as it cools, and the blue temperature is the temperature of the water bath as it cools. I'm going to constantly stir the naphthalene or periodically stir it as it cools, and you're going to record the 2 temperatures, both of the naphthalene in red and the water in blue, every 30 seconds. So you can begin timing at any point you like at this point, and we're just going to go for every 30 seconds until the temperature drops to the low 70s. So you should have started timing. You're filling in a data table now with the temperature being recorded. Every 30 seconds, if you're making your own data table, then you could choose whichever time interval you like, 20 seconds or something like that. Perhaps even every minute. This is not going to be the most exciting YouTube video to watch. When we do this experiment in a lab, it's not the most exciting experiment to do either. Students are staring at thermometers. When we measure both the water bath temperature and the chemical temperature, one partner would read one thermometer, the other partner would read the second thermometer. We've got the test tube sitting in a hot water bath simply so that it cools more slowly than it would have cooled in the air. If I just had the test tube sitting in the air, it would cool much faster. Your graph that you get, the cooling curve wouldn't quite be as good. It's important to stir the naphthalene consistently so that the cooling throughout the chemical is consistent. Again, be sure you're recording your temperatures at regular intervals. This lab was recently done here. Some students actually did this in the lab, and there's at least 2 test tubes that are broken and naphthalene spilled into the water baths because they were stirring too vigorously with their thermometers. So you will be making a graph with both of these sets of data, both temperatures being plotted on the same graph. I don't know if you can see in the video, but there are little white crystals forming inside the test tube right now. A little cloud of white crystals are forming as I stir. That's evidence, visual evidence, that the naphthalene is starting to freeze. Okay, so we're stirring at a constant rate. Crystals are getting a little bit cloudier. I'm not sure if you can see that if you look carefully in the video. This is actually my second attempt at this. I did the experiment yesterday collecting data, but I did not stir consistently. When I looked at the data later, I was really unhappy with the shape of the graph produced. Without stirring, I didn't get a nice plateau in my graph. So here I am the next morning at school for your benefit, doing a boring experiment a second time. And you are watching a boring video, recording the temperature every 30 seconds. Now, if you're thinking about the numbers as you write them down, you might think that there's something wrong. Notice that the water temperature is still cooling, while the chemical, the naphthalene temperature, has been somewhat steady. We also know that the naphthalene is freezing because we can see the crystals in the test tube. We're now coating the test tube on the inside. The water is not freezing. The water is simply cooling. Water will freeze only when it gets down to 0 degrees Celsius. So think about what the shape of this cooling curve will look like for the naphthalene versus the water. Now, if we had time, we might even collect the temperatures until it cools all the way to room temperature. But we're not going to do that. Ideally, we'd like to see the naphthalene cool down to around 70 or 72 degrees Celsius, in that range. Right now, the stirring is getting a little bit more difficult because the naphthalene is freezing. I can still stir, but there's more and more solid naphthalene in the test tube, less and less liquid. Hold the test tube with one hand and stir with the other. Now, sometimes as a chemical cools, you'll see in the graph of the cooling curve evidence of supercooling. We call it a liquid that remains a liquid even though the temperature has dropped below its freezing point. So it hasn't started to freeze even though the temperature is below the freezing point. We say that that liquid is now supercooled. It's highly unstable. The particles, the molecules in the liquid, or the atoms in the liquid, if it's an element, they haven't yet begun to take their positions in a crystal lattice structure. It's sort of like people milling around in the classroom, in and out of the chairs between the tables. As you cool the liquid, the people are slowing down. When you reach the freezing point, they're supposed to sit in their chairs. That's like the molecules or atoms taking up their positions in a crystal lattice. But it takes some time for everybody to find their own seat and sit down. During that time, when the particles are trying to find their positions in a crystal lattice, the temperature can drop below the freezing point, and that's supercooled liquid. But when they take their positions in the crystal lattice, the molecules or the atoms will then create intermolecular forces. Little bonds will form between the molecules, the particles, and that releases a little bit of energy, and so the temperature will then rise again. So after it was super cooled, the temperature will start to rise when the freezing actually begins. And then when it reaches the temperature of the freezing point, the temperature, as you saw in this graph, in your data, the temperature will then remain constant. So on a graph, if you see a little dip in the temperature before a plateau where you expected freezing to occur, that little dip is where supercooling occurs. The freezing would only begin at the lowest point on that dip, where it starts to rise again. When the temperature starts to rise to the freezing point again, that's where the freezing began. Now eventually the chemical in the test tube will be completely frozen, be completely solid. At that point, the temperature should start to change again. So I'm going to stop stirring just because the temperature here is becoming, the solid is becoming pretty homogeneous. The test tube has got not a lot of liquid left in it. I'm going to stop stirring, and you should see the temperature plateau for a little bit longer, and then it may start to decrease. But notice the wide range in temperature at this point. The water has cooled down to the low 60s, while the naphthalene, which has been freezing, you can see the white solid in the test tube now, is still up close to 80 degrees Celsius. When the naphthalene finishes freezing, when it's completely frozen, then the temperature will start to cool down, and it would cool down eventually to room temperature. When the two temperatures reach room temperature, they won't continue to cool below that. So if you did collect data all the way to room temperature, you would see another plateau in the graph. But that plateau is not a phase change. That plateau represents the fact that you've reached room temperature. So don't be tricked by that. If you see a cooling curve and you see a plateau around 20 degrees Celsius, that's likely due to simply having reached room temperature. The thermometer is almost impossible to stir inside the test tube at this point. It is pretty much frozen solid. So we see the temperature now, the red temperature, the naphthalene starting to cool down. It would be nice if you collected enough data to see your naphthalene's temperature plateau finish and the temperature start to cool down again after the plateau on your graph. If you run out of room in a data table, you can add some extra rows beneath it, or even in the margin you could add some extra data there if you need to. But it's getting now below 77. We'll keep cooling it until it gets to be in the low 70s. If you're making a graph by hand, it looks like the water temperature is going to be below 60 degrees Celsius, so you'll probably want to start your temperature scale at around 50 or 55 degrees Celsius. And going by memory, I think our starting temperatures were just a little bit below 90, so on your temperature scale you'll want to go up to at least 90 degrees Celsius to show all of the data. Alright, so the naphthalene is now cooling down significantly. The rate of cooling is reasonably fast, partly because it's sitting in a water bath, which is 15 degrees, 16 degrees lower temperature. So the naphthalene is cooling somewhat fast at this point. All right, so we'll go just for a few more seconds. You could collect one or perhaps two more data points if you like. So let me just show you the test tube with the naphthalene. It's now completely solid, white, crystalline solid. It originally was a colorless liquid when it was melted. Keep in mind that freezing does not mean cold. This chemical was freezing at the temperature above 70 degrees Celsius. So even though it was hot by our standards, it was freezing, right? Freezing is simply the phase change when a liquid becomes solid, when the liquid particles are slowing down enough that they take up positions in a crystal lattice structure. All right, I'm going to stop here. You've got lots of data there to create a good cooling curve for the naphthalene. If you see, and of the water, if you see any evidence of supercooling on your graph, you'll want to indicate that, label it. You can indicate on the graph the different phases, liquid, liquid and solid. If there was a phase change, in this case freezing, you can indicate where that occurred on the graph. All right, there you go. Congratulations, you've just watched a long, boring YouTube video to replace a long, boring science lab.